Hi there, this is Math 6, Unit 1, Lesson 17, called Squares and Cubes. And so we're going to be investigating today perfect squares and perfect cubes. And so here we go. All right, first of all, first activity says the number 9 is a perfect square. All right, find 4 numbers that are perfect squares and 2 numbers that are not perfect squares. Okay, so when we're talking about a perfect square, what we're often talking about is taking two numbers and multiplying them together and then finding out what that result's going to be. So something like 9 is a perfect square because 9 is the product of 3 times 3. And so when we look at a square and actually draw a square, we can see that a square that is 3 units by 3 units long is going to become a perfect square. And that's where that term kind of comes from, right? So there's our square, and it's a 3 by 3 shape, quadrilateral, that ends up being a perfect square. So are there other examples of what a perfect square could be? And to answer that is, yes, there are many other examples that would give us a perfect square. So, for example, you could have a square that is simply a 1 by 1. And a 1 by 1 would get you a perfect square, and so the perfect square number, 1 times 1, is actually 1. Okay? If I had a grid and I had a 2 by 2, like this, I know that's not perfect, but a 2 units by 2 units there, 2 times 2 is 4, and so 4 is also a perfect square number. We've already shown the 3, right? But we can also do 4. And so we draw this, cut this up into 4 equal parts like so, to give ourselves a nice square. That's a 4 unit by 4 unit, and 4 times 4 gives me an area here of 16. So 16 is also a perfect square. All right. Are there more? Yep, we can keep going. So anytime you multiply this out, right, we could do a 5 by 5 square, and that would become a perfect square of 25. And so on and so forth. So we can continue that on for a long ways to go, right? So these are all examples of perfect square numbers. 1, 4, we can add the 9 in there, 16, 25. A square has a side length of 7. What is its area? So because it's a square, we know that each side has a side length of 7. And so 7 times 7 would give me the area, and 7 times 7 becomes another perfect square number, which is 49, right? And it's kilometers, so we'd say 49 kilometers square. Looking at number 3, it says the area of a square is 64 square centimeters. So we've already figured out the area, right? So you have a square, it's a perfect square of some sort, and we know the inside space is 64. So to find the side length, we need to ask ourselves, which two numbers, or what number, can you multiply by itself to come up with 64? Well, so far we've seen what 1, 2, 3, 4, 5, 7 work out to be. So 7 times 7 is 49, so we know we need to get to 64. And hopefully in 6th grade we know that 8 times 8 is 64. So we would need to have a side length of simply one of those. 8 centimeters would be the side length to end up with an area of 64 square centimeters there. That's the idea. Alright, activity number 2 is something that you'll want to do in class with your teacher if you haven't already, right? And it says your teacher gives you 32 snap cubes. So a whole bunch of little cubes looking like this, right? 32 of these guys. You want to use them to build the largest cube you can, and each small cube has an edge length of 1 unit. So using 32 of these, we want to create the largest cube we can. So again, not going 1 by 1 because that's not going to be the largest we can, and probably even going if you went one lengths of 2, you can end up going a 2 for the base there. Now this isn't a cube yet because with a cube what do I need to do? I also need to get the height to be the same as well. So to make this a cube, I want to go ahead and actually add a whole nother layer on top, something like this. And so with a cube, I would end up with a 2 by 2 by 2 shape. Alright? Let me draw that out real quick what that would look like, because here's my 2 by 2. So if I had a cube and I went like this, we just drew a quick little sketch of a cube here. If I had a height of 2 and a length of 2 and also a width of 2, that's going to be a total of, in this case here, we can see we used 1, 2, 3, 4, 5, 6, 7, 8 cubes to do that, right? So using 8 cubes, I get that one right there. I want to try to use all 32 if possible, right? So let's say that I use a 3 by 3. Okay. Now if I use a 3 by 3, it would look something like this. A little bit like a Rubik's Cube, right? We have 3 by 3 by 3. Now when you look back at our 8 one, we went 2 times 2 is 4 times 2 is 8. So we did 3 by 3, that's how many cubes we end up using, right? So with a 3 by 3, how many cubes we use? 3 times 3 is 9 times 3 is 27. So we use 27 there. That gets us pretty close to 32. And so the question is, could I go further than that? Well, the answer would be, what you find out is, no, it'd be hard to make another layer with just 5 remaining cubes. Alright, so when I did this one, and do it with the snap cubes yourself, you can take 27 snap cubes to make a 3 by 3 by 3 cube, just like a Rubik's Cube might be. Okay? So what is the edge length of each of the cube you built? We would say it's 3 units long. Okay, and so again that would look something like, be this long here. That's great, but it's also going to be this wide. We're going to go 1, 2, 3 out here. 1, 2, 3 this way. But we also know that we have to go high. So perhaps we go up here. And we're going to go 3 by 3 by 3. Something along these lines here. So we have a 3 by 3 there, we go 3 down this direction, and we go 3 down this direction. Alright, okay, so something along those lines there, and if we filled in the spaces, we'd get ourselves a nice cube, and it would take 27 snap cubes to do that. Okay, so what is the area of each face of the cube? Well, each face of the cube, we put that together there. 1, 2, 3, and we can go 1, 2 more here. Put those together. So the area of the face of the cube would look something like this, right? So that's going to be 1, 2, 3 by 3. So the area is drawn like this, 3 times 3, and 3 times 3 is 9. Okay? So we have an area of 9 units squared for that one there. And in terms of the volume, because we would do this 3 times, because we're going to have a height there, 1, 2, 3, we would do a volume of 3 times 3 times 3, right? Or we take that area and we're multiplying it 3 times for a total of 27 units cubed, we say, because we ended up making a shape of a cube. Alright? Our cube units, however you want to write that out. Okay, that's the idea of building cubes there. So that leads us into the next activity, number 3, which says the number 27 is a perfect cube. So just like we talked about a perfect square being 2 numbers you multiply together and arriving at that number there, a perfect cube is when you take the same number and multiply it by itself 3 times to make a perfect cube. Here is our 3 by 3 by 3 cube. It says find 4 other numbers that are perfect cubes and 2 numbers that are not perfect cubes. Okay, so let's go back to what we know. For example, we know we could do a 1 by 1 by 1, and that's going to equal 1. So 1 is also a perfect cube. If I had side lengths of 2 by 2 by 2, like we drew up above here, that's a perfect cube of 8. We've done 3. I could do a 4 by 4 by 4. It gets a little bit larger there. And a 4 by 4 by 4 is 64, so 64 is a perfect cube. And finally I can do a 5 by 5 by 5, and that's going to be equal to 125. So those numbers, as well as the 27, are all examples of perfect cube numbers. Number 2, a cube is a side length of 4. What is its volume? So volume here with a cube is going to be that number, right? So here's our 4. So a 4 centimeter thing would be 4 times 4 times 4. That's going to equal 64 cubed centimeters. because we're doing the centimeters and we're doing it cubed. Number 3, a cube has a side length of 110 inches. What is its volume? All right, so that's going to be a 10 by 10 by 10. So 10 times 10 is 100. 100 times 10 is going to be 1,000 cubic inches there. And finally, number 4, a cube has a side length of s units. What is its volume? Well, that's going to be s times s times s, right? Got that there? So s times s times s. And so we have s times s times s, cubic units, and there we go. Okay, so it's s times s times s times s, cubic units, looking something like that. Okay, and that's it for that side there. Okay, now this question here leads us into the next activity, because we probably don't want to write that out quite like that. There are some other things we can be doing here. And so I'm going to leave it like that for now, and let's move into, well, let's talk real quick as we move into it. Have you ever seen something that looks like this? Okay, well, what does this stand for? What does this represent? We've seen perhaps before maybe something like s squared. This is an s, not a 5. That's just s. So s squared means what? It means the letter s times the letter s. Okay? S cubed means s times an s times an s. So we call these numbers up here exponents. And so essentially, when we look at this, this is like s to the number first power, s to the first power, s to the first power. And when we add those up, we end up with s to the third power. It's like we've been talking about when I do something with the inches over here, for example. Okay, I have an inch as a unit, an inch, and in the end I end up with cubic inches. Why? Because I have an inch times an inch times an inch, 1, 1, 1, and 1 plus 1 plus 1 is to the third, so I end up with the cubic inches. So the 3 means that I'm going to be here cubing it, whereas a 2 means I'm going to square the number. I'm going to multiply by itself 2 times there. And that's kind of the idea, right? So for example, if I have 5 times 5, 5 times 5 can be rewritten as 5 squared. That's squaring the number there. If I have a 4 times 4 times 4, that means I'm multiplying the number by itself 3 times, or I am cubing that number, 4 cubed. Okay, so I have squaring, and I have cubing. So here we want to take a look at how those exponents work out here. So the square has a side length of 10 centimeters. Use an exponent to express its area. That means leave the exponent attached. So area, with an area, we're going to be finding just the square of it, right? So this would be 10 squared centimeters squared. Why? Because the area is going to be 10 times 10. Or realistically, what I probably should write for you is I should write down 10 centimeters times 10 centimeters. And so the two 10s become 10 squared, and the centimeters become centimeters squared. Okay? It says the area of a square is 7 squared square inches. What is its side length? So thinking about the other way, we say, well, the area here is 7 squared. Well, to find the area of a square, we're going to multiply this and this, those two numbers together, the length and the width. So, but those numbers together is what forms this number right there. So our side length would just be 7 inches. Because what we're doing is we're saying 7 inches times 7 inches is 7 squared inches. So just working backwards from what we did with number 1. For number 3, now instead of saying, kind of step by step here, right? We took the 10 and we turned it into a 10 squared. We took a 7 squared and broke it back into the 7. Now look at this one. It says the area is 81 meters squared. So notice this is just the number itself. Something has already been squared to leave us with 81, like our answers in previous problems. So use an exponent to express this area. So we want to turn this into an exponent number, like up here 10 squared. So instead of saying 81, how can we turn 81 into a number with an exponent? Think about your square numbers there. We knew that before. 8 times 8 was 64. So if we continue to go up, 9 times 9 is 81. So 81 is a perfect square. So we could say that 9 squared is the same as 81. So I'm replacing the 81 with a 9 squared, and I keep the meters squared the same. So we're just moving things around, or changing numbers back and forth into being an exponent or not being an exponent, but it means the same thing. So this is the part for area on this side here. Now let's take a look over here at some stuff we would do with the volume. Same idea. It says a cube has an edge length of 5 inches. Use an exponent to express its volume. So that means we're doing 5 inches times 5 inches times 5 inches. So to make that as an exponent, how many 5s do I have? I have 1, 2, 3. So 5 cubed, and my inches, I have 3 inches. So 5 cubed inches cubed is that volume written with exponents. Look at number 5. They already have a problem written down that way. 6 cubed centimeters cubed. What is the edge length? So now we need to go back the other way, right? When we looked at the 5, the edge length was what we did 3 times in a row to get us that. So here, 6 cubed centimeters cubed, if I just kind of extract one of those out, the edge length becomes 6 centimeters. Why? Because 3 of those gets me to there. And then finally, a cube has an edge length of s units. Use an exponent to write an expression for its volume. Alright, so we want to do the volume, and we know it's s units. So that's going to be an s unit times an s unit times an s unit. Or, with exponents, s cubed units cubed. And that's the idea. We'll play with exponents a lot more, but this just kind of get you going with that, get you an idea for how that works there. So, in summary, today, when we multiply two of the same numbers together, that is squaring. Just like 5 times 5 is 5 squared. When we multiply 3 of the same numbers together, that is cubing. Like 4 times 4 times 4 becomes 4 cubed. We also use this notation for square and cubic units. So we can see we have things like inches squared, centimeters cubed. So the units are there before. There as well, not before. So we can read this a couple ways, which is where you might want to just kind of pay attention here a little bit, because when you read things or say things, you might hear people talking about 25 inches squared, and they might say 25 square inches or 25 inches squared. So depending on what you do, this is the way you write it out, but sometimes you say it this way. So you actually kind of reverse the way you say that. The same thing with the cubing part as well. So just kind of make a little mental note of that, because you'll hear it said differently than the order that it's written in. Okay? So that's it for today's lesson. We're going to pause there and give you a chance to work on your homework, and we'll see you back here in just a couple seconds, or minutes, or hours, or days. Okay, homework for lesson 17, Math 6, Unit 1. What is the volume of this cube? Volume is found by multiplying the lengths that were given, the edge lengths of the cube. We have a 2 by 2 by 2. So I can write this as 2 centimeters times 2 centimeters times 2 centimeters. Now if I combine those together, I know that if I wrote it with exponents, I have 2 cubed times centimeters cubed, if I wrote it with exponents. But I'm not done quite yet, because I do want to find the volume. It doesn't say leave it in exponents. So 2 cubed means 2 times 2, which is 4, times 2, which is 8. So I'd write this as 8 centimeters cubed for number 1. Okay, those are steps there. Number 2, decide if each number on the list is a perfect square. So if it's a perfect square, then that would mean that it's a number like a 2 times a 2 to give me that perfect square number. So is there one number you would multiply by itself to come up with these numbers here? So first of all, we have the number 16. I'm going to zoom in a little bit here. 16. 16 can be broken apart into what? 4 times 4. So that works out great. 20. For 20, I can think of 10 times 2. I can think about 5 times 4. But I can't think of a number by itself. So 20 is not going to work. C. We have 25. Well, I know that 5 times 5, that works out great. For D, we have 100. 100 is going to work because why? 10 times 10 is 100. For 125, well, if 10 got you to 100, I might have to go up and go 11. Well, what's 11 times 11? 11 times 11 is 121, so it doesn't quite get me there. Not going to work. 144 looks bigger than 11, and sure enough, 12 times 12 is 144. That works out as well. When you get to 225, now we're talking about some larger numbers, and you may not know your math facts for things like 13 times 13, and 14 times 14, and 15 times 15, but this one actually works because 15 times 15 is 225. So that is one of those extra little numbers that you might see come up in different math lessons throughout the next several years, just as one you might want to kind of put in your back pocket and know. And then finally H. H is 10,000. And what's interesting about this is if you take 100 times 100, and we just put all those zeros together, that's 4 zeros, 1, 2, 3, 4. What do you end up with? 10,000. So H would work as well. So write a sentence that explains your reasoning. So on these problems here, remember, I don't usually write it out. I let you write out your thinking, but I'll talk you through it. And so our idea with B is that perfect squares are found when you multiply a whole number by itself, right? Something like if I do 2 times 2, when I multiply a whole number by itself, it gives me a perfect square. So write out some kind of sentence there. Don't write that. That's not going to be a good answer because that's not a sentence. Okay, number 3. Decide if each number is a perfect cube. Now remember, a cube is when you multiply a number by the number by the number, right? So 1 actually works just fine. 3. There's not a number that can get me there. 8. 8 becomes 2 times 2 times 2. That works out just fine. 9 is here. You're kind of thinking, well, does it work? Well, what's after 2? After 2 comes 3's, and 3 times 3 is 9, but 3 times another 3 is actually 27. 3 times 3 times 3. So 9 won't work. 64. Well, let's see. 4 times 4 is 16. And 16 times 4 is actually 64. That's going to work. For this one, not going to work here. Why? Because we know that that's to 10 by 10. And if I do 5 times 5, that's 25. 25 times 5 is actually 125. So if 4 gets me to 64 and 5 is 125, then 100 is out of the question. So what's a perfect cubed? Again, it's right here. It's when you take the same number and multiply it by itself 3 times to get that perfect cubed number. Number 4. A square has a side length of 4 centimeters. What is the area? So to find the area, we would do the side length of 4 centimeters times the side length of 4 centimeters. That becomes 4 squared centimeters squared. And 4 squared is 16. And centimeters squared just keeps its name, and that's what we have. Number 4b. The area of a square is 49 meters squared. What is the side length? So we can see we're going to square something to get meters squared. So what number can you square to get 49? Helps to know your math facts here. And we would say 7 meters. Because why? 7 times 7 is 49. For C, it says a cube has an edge length of 3 inches. What is its volume? So that's going to be asking us about 3 inches times 3 inches times 3 inches, because volume is going to be the multiplication of the height, the length, and the width. So that becomes 3 cubed inches cubed, because there's 1, 2, 3 of those, and 1, 2, 3 of those. And 3 cubed is 3 times 3 is 9. 9 times 3 is 27. So we have 27 inches cubed, right like that. Alright, number 5. Turn the page here. says prism A and B are rectangular prisms. Prism A is a 3" by 2" by 1". Prism B is a 1" by 1" by 6". Okay, so let's just write this out real quick a different way. So A is a 3 by 2 by 1. B is a 1 by 1 by 6. Okay, just make sure I have that right there. Select all the statements that are true about the two prisms. They have the same volume. Okay, well, volume would be all three multiplied together. So let's take a look here. So volume of this one is 3 times 3 is 9, times 1 is still 9. That works out okay. The volume of this one would be 1 times 1 is 1, times 6 is 6. So they have the same volume there. What am I doing? Oh, I'm so sorry. I'm like, what am I doing wrong? I made a little mistake in my notes. So sorry. Back it up there. Oops, that's a 2. Make that a 2. 3 times 2 is 6, times 1 is 6. Yes. So, are the volumes the same? Yes, they are. They have the same volume. The volume equals 6. Okay, so 6 inches cubed. Perfect. They have the same number of faces. That's going to be a yes, but why is it a yes? It's a yes because they're both a rectangular prism. It's the same shape. So, with being a rectangular prism always has 6 faces. That's what makes a rectangular prism, as well as the shapes that are in it. So that's going to be true. C, more inch cubes can be packed into prism A than prism B. When we're talking about filling something, filling is dealing with the volume. So inch cubes in one box versus the other box are going to be what? They're going to actually be the same. Why? Because the volumes are the same. So that's not true. The two prisms have the same surface area. Alright, so surface area, that's going to be a little trickier. Okay, so surface area is a little different. Surface area, we're going to have to look at the different lengths they have. So for the surface area, we have 3 times 2 for this one, which is 6. Let's see, maybe I'll draw it out for you real quick, right? So here is a 3 by 2, and we'll make it a 1 there, by 1. And over here we have a 1 by 1, and we'll make it a 6. So 1, 1, and 6. So for shape A, we have 3 times 2. This front face would be 6. There's 1 on the back. We'll get there in a second. This side right here is a 3 by 1. It's a 1 length right there. So that's 3. And the top is a 1 by 2, which is 2. So the surface area so far of 6 and 3 and 2 is 11, but double that, so it has a surface area of 22. Over here we have a surface area 1 by 1 is 1, and then we have on the top a 6 by 1, which is 6, and then we also have on the side a 6 by 1, which is 6. So that's going to be a total of 13, but I have double sides, so that's going to be 26. So surface area is 26 for that one there. Oh, did I run off the table page again? Sorry about that. Back you out a little bit. There we are. So surface area is not the same. The surface area B is greater than A, and here's B. We said B was 26 and A was 22, so that would be the true statement. So number 5 was a long problem, lots of things to do there to find the surface area and the volume of two different rectangular prisms. But that's something you got to be able to do for this unit, and we're getting to the end of it anyways. Number 6, what polyhedron can be assembled from this net? Well, we see that we have a collection of triangle shapes here, and 1, 2, 3 rectangular type of shapes. So we can say that we can once again form a triangular prism. I think that's been an answer to a question on all your homework for the last 4 or 5 lessons. B, what information would you need to find its surface area, and be specific and label it as needed? So to find the surface area, we would need to know the height of this. We have to know some numbers, right? How high that is, how wide that is, this length here. We would have to know all of the side lengths. That's the big thing. We can't find the area if we don't know the side lengths. Impossible. So you'd want to label this up and say, what are all these side lengths here, to know what that surface area could be. Alright, and finally number 7, find the surface area of this triangular prism, which is on the back side, and everything is in meters. Let's see here. We want to find the surface area. Surface area in meters. So we're doing the surface area in meters. All right. So surface area in meters. What do I have? I have a few different shapes here. Okay. First of all, I see that I have a triangle right here. Okay. This triangle has and it's the front and the back, right? It has a base of 1.2, and the back side we see that its height is 0.8. That's a triangle there. So to find the area of that triangle, that would be 1/2 of the base times the height, but that's also times 2 because it's front and back. So knowing that's times 2, 1/2 times 2 is 1. So I really have 1.2 times 0.8, which when you multiply that out there, 1.2 times 0.8, we end up with 0.48, right? Yeah, 0.48. I feel like I'm doing something a little off there. My notes are a little different. Sorry, 1 second. Pull out my calculator to double check that because I was not using a calculator. Just looking at my notes, 0.08, 1.2 times 0.8 equals, wow, that's a crazy number, 1.2 times 0.8 equals 0.96. That's craziness. Okay, let's try to check this. 1.2 base times height, 1/2 of the base times height, and so that becomes, yeah, 0.96. I'm sorry, 0.96. My notes, I didn't do the times 2 of my notes, so I would do 0.48, which is half of that, and then multiply it by 2 later. So the 2 triangles is 0.96. Great. Now let's take a look at the different rectangular shapes we have. We have one with a base of 1.2, and it has a length of 1. We have this side, which has, again, the length of 1.2, and then a length of 1. And then I have this one on the bottom, which is actually more of a square base, which is a 1.2 and a 1.2. Well, that's not very squarish, right? But that's a 1.2 and 1.2. So this base is 1 times 1.2, which is 1.2. This is 1 times 1.2, which is 1.2. And then 1.2 times 1.2 is actually 1.44. So I have all these shapes. I got to add up now. 0.96 times plus 1.2 plus 1.2 plus 1.44, all combined to be 4.8 meters squared. And you add all that up there. So surface area of that triangular prism, after all my little mess ups, becomes 4.8 meters squared. Is it okay to mess up the math? Sure it is. Just go back and fix it and check it again and again until you get it right. That's what makes it fun. Have a great day. We'll see you next time.